In this next module, we're going to be talking about a technique that will make the calculations associated with analysis of indeterminate beams and frames go much quicker when processing by hand. Now 30 years ago, and 40 and 50 years ago, this was a particularly important technique because computer models were not all that easily accessible, and etc. These days, the reason why we still talk about the moment distribution method is because it highlights some very important aspects of the behavior in a structure, and that the numerical steps that we're going to take mimic a little bit about what the structure is doing as it comes to equilibrium under the applied loads. And so things such as the distribution factors and these carryover factors and what the relative stiffness, all these kinds of things are particularly useful ideas to understand what our computer models are, what's going on in our computer models. And as well, if the moment distribution method becomes a very efficient technique for doing isolated aspects of a more complex structure's performance, and particularly, let's say we have a structural model of a very large system and we're trying to make sure that we've done data entry correctly, and we can do some simple things here that become very powerful in helping us to understand what might be going on in the larger model, and whether that work is at all anywhere close to being valid. So we're going to set up this moment distribution method and some of the underpinnings, and there's going to be some other key kinds of aspects of things that we'll look at in the first example. And examples 2 and 3 will be really focused on special applications to beams, and then we'll get into some frames after that. Of particularly important significance in multiple ways is going to be this fixed end moment table that you can find in all kinds of different sources, but this notion that in isolation we're going to be looking at our beams as though they are temporarily fixed, and we apply the loads, and then we're going to start to sequentially release a joint, let it rotate, come into equilibrium, and then we'll lock it back down and go to another joint, release it. That's effectively what we're doing in the moment distribution method until we get a structure that is at equilibrium. So let's get right into the heart of it here. Well, let's take a look at first at a slope deflection viewpoint of a two-span beam. The span lengths are the same, but they have different bending rigidity, and we only have a load applied at the midspan of one of the particular ones, and in the stiffer one. And we know, of course, from the slope deflection approach that in this kind of situation, without any chord rotation, we've got 3 potential kinematic degrees of freedom: theta A, theta B, theta C, the rotations at each of the joints. So with that at work, we know that we're going to end up with some sort of a 3x3 global system by the time we're done. We're doing the analysis. We take the I's over L's of the member, and the second member has twice the stiffness. There's no fixed end moments in member AB, but we do in BC, and with the midspan load, that's plus and minus PL over 8, which turns out to be minus and plus 100 kilonewton meters, the minus being on the left, the plus being on the right. We know that we write the slope deflection equation for each and every member n. I've already removed the chord rotation terms since they're all 0, but nothing else is. We're not using modified stiffness yet, so we're just writing the general expression here. Of some level of importance of truly thinking ahead, it's particularly important and useful to begin to realize that these equations that we've written, the moment at the near end and the moment at the far end of the member, are as a function of these member end and chord rotations, and then the fixed end moment terms, that superposition of all 4 terms that we've got in the general expression, can be rewritten in matrix form. This particular one would be associated with the local situation. I know that because of the lowercase symbol for these stiffness coefficients. That's what I'm really setting up here. Is in a very short time we'll start talking about a direct stiffness approach as opposed to the slope deflection or moment distribution approach, which are all under the same category of the displacement method. called the displacement method because, of course, the unknowns in the equations that we're solving are the displacements. We're writing equations related to force terms, in this case all moments, and these are the unknown displacements that we are actually calculating here. Right? And again, it's a useful thing to be thinking about how this would look in a matrix form. Remember, we're going to get then from a global standpoint the big picture equations of equilibrium by going to each degree of freedom, writing what the moment equation might be. We want to get those in terms of the member end moments because we'll turn that into then an equation that involves the member end displacements. Again, do that at A, B, and C, and we've done this many times before. I've here aggregated this all together into this matrix form. Right? Again, this is a key kind of viewpoint to begin to understand as we get later for the formalization of what turns out to be how computers are behind the scenes doing their work. And so this big square matrix is our global stiffness matrix, and we've got these off-diagonal terms that will oftentimes be zero, and we'll talk a little bit more about why that might be the case in a moment, and no pun intended, because this is an equation of moments after all. And note that in this middle term we have a summation of a couple of stiffness terms that are sitting there, as well as what happens generally speaking in this force vector that used to be on the left hand side, but we took it over to the right hand side, hence the minus sign that shows up. And since we didn't have any joint applied forces, there's nothing else to add to this. Now in this particular problem, yes, the AB and BA terms are going to be zero, but this is written here just to be in as general fashion as possible. Right? And so now we can solve for that, the member end displacements, by then inverting the stiffness matrix, post multiplying by the opposite of this fixed end moment or fixed end force vector. Excuse me. Once we have these, then we'll take those and we'll feed them right on in to back to the local system. So this is a global viewpoint here, and on that previous page we were looking at a local viewpoint. Uppercase for the global, lowercase for the local conditions, and selecting only the little pieces that matter for that particular member and feeding it back in. Now the thing about that is that for the most part we're going to calculate all these member end displacements for the sole purpose of substituting and calculating the member end moments and forces. We don't really want those. They're only a means to an end. Right? So we gather all these terms and we drop them in, we go calculate these things, and then we feed them back into this other thing. If there was only a way to sort of rewrite this, drop this all somehow back into this, we'd never actually have to calculate those. We could go directly at what those member end moments are. And that in many ways is what's really going to happen in the moment distribution method. And as we get ready for a numerical example of that, it's a little bit useful here, as well as important for the later big picture application of the general direct stiffness approach, that we go back and have another understanding of what the stiffness matrix is all about. Right? So we've got this original structural model. We've got members of only two, A to B and then B to C. Two members that connect together at joint B. And that's why you're going to see somehow a summation of two effects directly at B. And you don't see that happening throughout the rest of this matrix. And even note that because joint A is not directly connected to all this other stuff over here, that's why you see a 0 times a theta, or rather a 0 times a theta A term on this off diagonal and a 0 times theta C term, is because of something about that distantly related, or that distance kind of thing. Now, to make that a little bit sharper and precise, let's go look at a model isolated to a specific Kij, and the one I want to focus on is going to be the Ki2. Right, so that would be then the terms. Now I have to think about this myself. Ki2, I would be the row term, right? That would be this one times that. That would be 1, 2. That would be 2, 2. That would be 3, 2. That would be running over all the various k values. So that's going to be really running right through that second equation. Now that displacement pattern that we might begin to think about here, when we say Ki2, what we want to really be thinking about is that means theta A equals 0, theta B equals 1, and theta C equals 0. And you're like, what are you talking about? It means that. Well, put in your displacement pattern of 0, 1, 0. And what are you going to do when you go there? Well, what we end up then with is this column, right? And so you're like, I still don't know what you're talking about here. Well, what do we do to create an absolutely zero rotation over here at A? We come in, we put a fixed end, right? It's not about whether the structure was that way originally. It's that way right now. And then we'll do the same thing here, that we have to come along and we have to put some sort of restraint, or we have to impose forces so that we get this displacement field. And then we'll say let theta B be equal to 1. Now remember, clockwise is positive, so here's our unit rotation. Of course, we have to have a moment that is applied there at joint B in order to get that to happen. Now the curvatures that will develop in response to that will be something like this, and it's sort of easier to see when you do that. You're going to end up with moments at these far ends as a result, and we know exactly how much moment we're going to end up when we do that. Right, we're going to have 2EKAB is going to be associated with this first one, and you're going to have 2EKBC associated with the other far one. And here at MB, the total moment that we need is going to be equal to the sum of these two stiffnesses. It's really not summing the stiffness so much as we're multiplying that by a unit rotation. That's why I say that's what the value of the moment is. And that's why I say really when you put the displacement pattern of 0, 1, 0, really the Ki2s are the second column. I know I kind of talked about, well, Ki2 and that I could run from 1 to 2 to 3, and that sort of makes you think that we're working with this row, but really you're looking here at this column in terms of the physical interpretation associated with this displacement pattern. Right? Now, if you went and said, what are the Ki3s, then I'd be saying, okay, what are the forces at I associated with a unit rotation or unit displacement at 3? So there, we're talking about theta A equals 0, theta B equals 0, and theta C then equals 1. And I didn't pre-build a little drawing of our structure, so let's get that in there. Gonna sneeze. Excuse me. And in order to have no rotation at A, again we'll clamp it down. No rotation at B, clamp it down. And we have then a unit rotation at C. And so the right-hand member will look something like this, and the left-hand member, the left-hand member is straight because we've got it completely clamped. See, the far end A has nothing to do, has no direct connectivity to this degree of freedom over here that got rotated. Right, that was our theta C equal to 1. So therefore, that's why you find out you've got a 0, up here sitting in this term, because there will be no MAB necessary to hold anything into place. There's nothing going on, nothing's being changed in that particular member. On the other hand, we do have to impose a moment to make this happen, and that moment at that far end will be equal to 4EK BC, right? That's this one right up there. And then of course the other one is going to be 2 EK BC. Of course those are really times 1, but that's why we choose the value of 1. And that's what these, in a sense, what the real meaning of the stiffness coefficients are all about. And we could actually assemble directly this stiffness matrix based upon this interpretation. And that's partially what we mean by the direct stiffness method that we'll be talking about in a different module, but it's sort of set up partially with this idea of clamping things, letting something rotate. That's very connected to what we're actually going to be doing in the numerical aspect or numerical process of the moment distribution method. Are going to be very much similar kinds of ideas.